Hello and welcome to another video. So in this video, I'll be explaining to you about metals and their reactivity. So basically in episode 10, I've already explained about electronegativity and first ionization energy. So I did talk a bit about metals, and now I'll go a bit deeper into explaining their reactivity of metals. And this is actually something important as well, so that's why I made this video. This is episode 11. So episode 11, reactivity of metals. So basically, if you have watched my other videos in this series, you should have already know the periodic table and the trends. So we have group 1, group 2, 3, and so on. We have many kind of different periods. So there are some common metals such as potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, copper, silver, gold, and platinum. Well, these are common metals, and basically there's a trend among them in terms of reactivity, like how they react. So when we talk about reactivity of metals, we often talk about their reaction with water, with acids, or with oxygen. I mean, there could be more reactions, but these are the three most basic. Alright, so now let me just go a little bit to the trends now. So basically, when you go down the group on the periodic table, like for example, if you go from group 1, for example, lithium, sodium, potassium, rubidium, and so on. If you go down the group, the reactivity will increase greatly. And if you go across the period from left to right, let's say from sodium, let's say from sodium, magnesium, aluminium, what next? Oxygen. Well, basically, when you go from left to right, the reactivity will just decrease. And there's a reason for that. Well, we did these things by experiments, but there are basically reasons. Well, there's a reason for everything. So, well, if you go down the group, you can see on the periodic table, you can see that as you go down the group, their radius, the atomic radius, or radii if you want to be plural, the atomic radius will increase as you go down the group. So what does it mean? It means the distance between the outermost shell and the nucleus will increasing as you go down the group. So basically, the nucleus here and the outermost shell that contain the electrons that will react with anything else around its environment, increasing as you go down the group. And what does it mean? If the distance between the nucleus, which is positive, and the electron, which are negative, increases, their interactive force, the force of interaction between them, will decreases. And it's like you are further apart from, if you are far apart from nucleus, you are less guarded, and the bigger the distance between the nucleus and electrons, the more likely that this electrons is going to fall apart, just get out, or being affected by the environment. So what does it mean? As you go down the group, the electrons of the outermost shell becomes much easier to react with the environment because it's less guarded. So that is the reason why when you go down the group, reactivity increases. Now let's look at the second one. When you go from the left to the right across the period, reactivity decreases. But why? Well, as you look at the periodic table, there's a trend of atomic radius, or radii if you want to. It keep decreasing, right? So the same logic can be applied here. So as you go from the left to the right, the atomic radius decreases. So the distance between the outermost shell and the nucleus keep decreasing and decreasing. So as they are becoming closer and closer, that outermost electron shell, that electron of the outermost shell become more guarded by the nucleus, and hence it is much more difficult to get out, like to react with anything else in the environment. So that is the reason why, as you go from left to right across the period, reactivity decreases. Okay, so that is the theory and explaining why. Now let's go to the reactions. So let's talk about reaction with water here. So basically, normally group 1 metals like lithium, sodium, potassium, rubidium, something like that, they react. They actually do react quite like vigorously with water. Well, for sodium, for example, is a very typical example. If you put them into water, a piece of sodium metal, it will. It basically just floats around, it skates around, and then it bursts into flame, and there are a lot of bubbles of hydrogen gas being produced. Like you can see this reaction: sodium solid put into water liquid, and it will become bubbles of H2 gas, and the resulting solution has sodium and hydroxide ions in there. I can just write like this, or NaOH aqueous, but I like to write in ions form like here. Okay, now, so basically it reacts easily. However, if you look at other group like group 2 or group 3 and so on, the reaction becomes not so easy. Let's say calcium, for example, calcium group 2. It reacts very slowly, like it doesn't react at all in water, but it does react if you put steam, which is of course very high temperature water. And there's a reason why group 2 doesn't react very well. If you look at their electron configuration, you can see its outermost electrons. Look at it, look at it. So calcium has a 4s2, outermost shell, and this subshell 4s is basically, it's full already, and it will be more difficult to get this electron, this one down, out, compared to the case of like group 1a for potassium, for example. This one, it's alone, it's easy to give up these electrons, and this one go back to the noble gas configuration, right? So basically, for group 2, it's more difficult compared to group 1 in terms of reactivity with water because of that. So, well, that's about water. Let me try to explain this reaction a little bit. Now, so as the reaction proceeds, when you put the sodium into water, the electron of the outermost shell of sodium will basically be attracted to the hydrogen, which is positive. Electron is negative. This one is positive. It attracts here. And as the electron come here, the electron from this hydrogen already in this bonding will come to the oxygen. And then it breaks apart this bonding between the hydrogen and oxygen. So you have OH minus ion being formed, OH minus. And since the sodium gave up one electron already, it becomes a cation, a positive ion, a cation. And what happens to the hydrogen that receives that electrons? Well, it becomes a hydrogen radical, like this. It becomes a hydrogen radicals like this. And then it will try to find other hydrogen radicals in the environment. Let's say there are other hydrogen radicals in the environment, and they combine together to become H2 gas. So that is basically how it happens. The reaction happens that way. And like I said before, as you go down the group, reactivity increases. So sodium, it reacts quite vigorously, strongly. If you put potassium, if you put potassium into water, it actually explodes like a firework. It explodes like fireworks. And when you go down even further, like rubidium, oh my god, it explodes like a bomb. And don't even mention other ones like down below. It's gonna explode like a nuclear bomb. Well, so now let's talk about reaction with acids. No, sorry. I forgot to mention that group A actually reacts very well with water. Group 2 doesn't react very well, but it does react. Just take time. And sometimes you need to put heat in there to spark the reaction, to excite it, to make it happen easier. When you talk about transition metals, like for example, zinc, iron, copper, lead, silver, gold, platinum, well, I would say they don't really react with water. It's hard. Let's just say it's hard. Okay, let's move on to the case of reaction with acids. So acids, what are they? Basically, acids are something that can give away H+ to the environment. So when it reacts with acids, normally the reactions are stronger. It happens easier than when it reacts with water. What is the reason here? The reason is very simple. Water is a very weak substance that dissociates into ions. Like you have 10 million water molecules, maybe you have one H+ and one OH-. However, when you look at acid, like strong acids, the dissociation is often very high, like 100% for HCl, for example. 100% dissociation. So there's a lot of H+ in the environment to react. So that is the reason why reaction with acids are generally faster, stronger than reaction with water. Okay, let's look at this case. Aluminium react with HCl acids. So of course, these outermost electrons will try to get out to the hydrogen here, and as a result you have bubbles, H2 gas, and the chloride Cl- ions get out, and the aluminum becomes ions just get out like this. Basically it's Al3+ ions and Cl-, but I can just write like this. Now yeah, I can just write like this. You might ask me why I write fraction over here, because I'm just lazy. I can just multiply by 2 so everything become like whole number, integers. But sometimes I write fraction because I'm just lazy, okay? You can write like this or like that, it's up to you. So 2, 6, 2, 3, oh yeah. Now, well, most of the metals will react with acids, except from the case, I think, of lead. Sometimes it doesn't. Lead doesn't. As I remember, silver doesn't as well, but it does react with strong acid, like concentrated acids. But if you put weak acid in there, it doesn't really react. All of these these kind of heavy metals things, they tend to react very weakly or not at all with acids. Anyway, let's move on to reaction with oxygen. What is oxygen? O2. Well, if you have learned electronegativity very well, you should know that oxygen has the electronegativity of say 3.5. which is very high. So what does it mean? It just means that the oxygen attracts electrons very well from anywhere else. So it means when you put oxygen in the environment as gas, for example, it tends to suck away electrons from metals very well. Like for example, potassium. If you cut a piece of potassium out, immediately within a few seconds, that piece of shiny potassium solid will absorb oxygen immediately and become darker. So we say the potassium is oxidized in that oxygen gas. It's very fast. You don't even need heat, don't even need anything, just a few seconds. You cut it out and then immediately it reacts with the oxygen in the air. Because why? We know already that potassium is very reactive with water, right? As told you before. So now it reacts very, very strongly with oxygen as well, giving up its outermost electrons very well to the oxygen. And it forms oxides called potassium oxides. Well, most of the metals will form oxides except from, say, gold and platinum. Well, you can see other cases here. Group 1 react very fast. Group 2 slow and it needs heat. For example, calcium with oxygen become calcium oxide. Well, the reason why group 2 reacts slowly is exactly the same as I explained earlier. Group 2, these last electrons, it's hard to get out because it is being guarded by shielding effect by these electrons. Compared to the case of potassium, it's lonely, it's easy to get out. To become go back to the noble gas configuration. So group 1, very fast reaction. Group 2, slowly, and sometimes it needs help from heat. For transition metals, I would like to mention the case of iron, which is a very popular case. You know, when you put iron out in the open air, slowly it becomes rusty, right? It rusts out. And rusts are basically what? Iron reacts with oxygen slowly and becomes either iron 2 oxide or iron 3 oxides. Depending on if there's a lot of oxygen. If there's a lot of oxygen, it's gonna react and become iron 3 oxide. If there's less oxygen available, it's going to become iron 2 oxide. Alright. But some people may ask me, Johnny, what exactly is Fe3O4? We saw them in some of the old books. Well, it basically is just a combination of these two, Fe1 plus 2 is 3, O1 plus 3 is 4, it's just that. They combine them together, but in truth, there's nothing called Fe3O4, okay? There's nothing like that. It's just Fe2, FeO, and Fe2O3, okay? Now, so that's a reaction with oxygen. I would like to go to something called the Reactivity Series of Metal. It's called Reactivity Series of Metal because they made up this one so that we can see how the trends look like. So, of course, heavy metals, very not reactive, and we go up and it becomes more and more and more and more reactive. Potassium is the most reactive among them all. So how to remember this reactivity series? Well, you can make your own mnemonic. I mean, I know that one in Vietnamese already, but every country or every group of students, they can use their creativity to create their own mnemonic. How to remember this thing? Well, and of course, you can explain this reactivity series of metal in the same way that I explained these two sentences. The distance between the outermost shell and the nucleus, if it increase or decrease. Now, so that's the reactivity of metal. I hope it was useful. I hope it was useful for you. Please like, share this video with your friends, subscribe to my YouTube channel, and press on the bell next to the subscribe button so you can get notified about my new uploads, okay? You can also follow my Facebook, but please don't add me on Facebook as friends, okay? Thank you and see you in my next video. Bye bye.